So as we get more into modeling, we're going to need to be doing three things. We're going to be selecting a modeling method. We're going to then be selecting our covariates or predictors, also called our independent variables. And then we're going to be optimizing the coefficients or parameters of the model, also referred to as the parameter estimation step. I skipped over model selection because that middle one really is the model selection, but I would say it's all three of these steps put together. In other words, we end up at the end with several different models that we feel pretty good about, and then we select between those. You could generate a very large number of models during this process, and then you pick a few that are good, and out of that, probably one that you're going to move forward for future predictive work. Okay, so there are a number of regression modeling approaches we're going to look at in the near future. That includes CART, GLM, GAMS, and HEMI2, and Maxent. Each of these is a little different. And an important thing that I've learned in teaching this class and looking at this broad set of methods is that quite often the response variable drives which method you can use. So if you only have occurrences, you have to use something like Maxent or HEMI2, and those are predictive modeling methods. Otherwise, you're looking at density estimators or clustering, which aren't really predictive, but they show you the density of where there's lots of occurrences. If you have binary data, presence, absence, you're probably going to want to use a GLM with a logistic response. You might use CART, and we'll talk about why when we get into that, but most likely it's going to be a GLM. And then categorical data, you'd probably use a tree method, which is the CART, categorical and regression trees. And with continuous response data, you might use linear regression if you've got a linear response and you feel pretty good about that, but that'll probably be rare. You'll probably want to use a GAM or a generalized additive model because that works with virtually any continuous response, and it supports continuous or categorical covariates, so it's very flexible. And here's another look at that from the modeling method end of things. A GLM, your response can be binary or continuous. Again, tend to use it with binary or bimodal response. GAMS, virtually any continuous covariates can be continuous or categorical. CART, specifically the categorical part of categorical and regression trees is what I recommend. I don't really recommend them for regression. They can do continuous response. Don't really recommend it. We'll talk about why in a little bit. And then your covariates can be categorical or continuous. HEMI2 and Maxent, the response has to be occurrence, just points where something occurs, which is kind of strange. But it works, and you can either have continuous or categorical covariates with that. All right, so as we dive into this, you always want to be remembering what's the purpose of your model. Don't get caught up in the modeling process for modeling itself. Always be able to pull back and say, what's the purpose? Why are we doing this? Also, how do you explain the results? How should they be interpreted and used? Because if you use too complex a method, you may not be able to explain it to anybody. And as a part of that, who's going to use the model? Who's going to use its outputs? In getting more detailed about that, we need to make sure a model makes sense to you and experts in the topic. Can you take your model and explain it to someone who might be an expert for the species that you're modeling? Do the predictions make sense? Does it hold up to validation? We'll talk a lot about that. Is the uncertainty acceptable? We've already talked about that, and we'll talk more about it. And is it overly sensitive? Another one that we'll cover. Okay, so when we really start looking at how good is a model, especially when we're looking at it within against a particular data set, there's a series of performance metrics which we'll start talking about. AIC is by far the most common. You need to know about it. You need to know some of the elements of AIC, like number of parameters and likelihood. We'll also talk a little about root mean squared error. Response curves with sample data are something you will see over and over again in this class. And part of what you'll get out of this class is being able to look at a response curve and really quickly identify what's going on with it. We've already seen some. Residual histograms with min, max, mean, standard deviation, in other words, statistics around your residual histograms. Always remembering that these only test our model within the domain of our data. Okay, so we've looked at histograms of residuals in the past. They continue to be important, always will be. You always want to look at them, see if they're close to normally distributed. Is the mean 0, which it should be, otherwise we've got some bias in there, something strange going on. Check the min-max, see what's going on. You might get a sample way out there, which can be okay, right? You can have 1, that's all right, but make sure you're not getting too many out there. Standard deviation, what's the spread? That's the general method for how good our data is matching the residuals, or how good our model is matching the data, because that will result in small residuals. And again, these really describe the full range of sample values. Got to watch for those exceptional cases where you might have a few sample points that look like they're outside the norm. And are they anomalies, or are they something important that you might need to model with a different method? Okay, real quick on response curve. So a response curve is the modeling curve for linear regression, which we've been doing. It is that linear line that we've been drawing. We're now going to call it a response curve because it's the curve that predicts our response variable. So here we've got a prediction from the model on the response curve. We've also got our data. Also, I just use this graph to talk a little bit about extrapolation. When we're modeling, we try and only do prediction within the domain of our data that the model was created from. You can extrapolate outside of that, but we really don't know what's happening out there. This is the challenge with modeling things like climate change, where we're predicting in the future where we don't have data. So we just have to be careful about it. It doesn't mean you can't do it. There's just caveats associated with it. Real quickly on root mean squared error, because you will see it once in a while. It's a powerful tool for being able to look at how well our residuals are matching our prediction. And it is used heavily in engineering and some other fields, so it may pop up. It's very closely related to standard deviation. If you take a look at the math, what we've got is our prediction minus our data sample. So each of the residuals squared, and then we add those up, divide by n. So if we add all these up and divide by n, our number of samples, you can see we're kind of getting an average squared value for our residuals, and then we're taking the square root. So root mean squared error really gives you sort of an average residual value, or an average error coming from matching our data to our model. Okay, now we're going to really get into developing AIC and the theory around it, which is central to this class and modeling. And what's happening here is we really need a method to select the best set of independent variables and the best parameter values or coefficients. Now, the thing here is we can always build a model that's incredibly complicated. We need to, and really fits the data, but we need to find something that's a balance between fitting the data and simplicity. R squared only considers fit to the data. Well, that's because linear regression is pretty simple, right? It's a straight line with 2 parameters, so it can't get too crazy. So we didn't need this until we start getting into some of these higher level modeling approaches. This is an excerpt from Anderson, who wrote Model-Based Inference in Life Sciences. Excellent book. Please read it when you get a chance. It's pretty approachable. Please read this. Pause. Read this when you get a chance. Very important. Shorter quote from Einstein: everything should be made as simple as possible, but not simpler. So we're getting to this idea that we want a simple model, but not too simple. And that's represented by the idea of parsimony, okay? And parsimony represents that idea that we have this balance between complexity and fit to our data. So if we don't have enough parameters or enough model complexity, the model will be unrealistic, doesn't make prediction reliable. But if we have too many parameters, then the model will be so specific to our data that you still can't make predictions, right? So it's this balance in complexity and fitting to our data. That's represented by this graph, where over here we have very few parameters, okay? And we're going to be underfitting our model, because our model will then contain structure that's included in the residuals. In other words, there's still dynamics or stuff going on in the residuals that should be in our model, and it's not. At the other extreme, we have too many parameters, and now we've actually built our residuals that should be residuals and should be part of the error structure into our model. Okay, so it's overfit. Either ends of this will cause problems. We want to find a balance in the middle. Okay, so to develop AIC, we need to first talk about likelihood. Likelihood is how likely that a set of parameters given some observed data, okay, or sorry, how likely a set of parameter values given some data, how likely that is, or how likely our model is to fit that data. The opposite of that is the probability of our observed data occurring given the parameter values. Now, that's kind of weird, but what you can think of it as is the likelihood is how likely our model is going to predict our data, or how likely our data fits our model. It's a simpler version of it. Okay, and some definitions before we dive into this. X is all of our sample values. X of I is one sample values. Theta is our set of parameters. And then P, X bar theta is the probability of X given theta. Okay, now, don't freak out on me. This is one definition for likelihood. So given some data X and parameters theta, we can say that the likelihood of theta given the data, remember we can either do it as likelihood of the data given theta or theta given the data, okay? That can be equal to the probability of, here it is, X given theta, okay? That can be expressed as multiplying together all of the probabilities of the individual data points given the parameters, okay? And then I just wrote that out as x1, x2, x3. In other words, probability of x1 given theta, probability of x2 given theta, times probability of x3. So we're multiplying the probabilities, each of our data points given a certain set of parameters. Using that, we can compute the likelihood. Now, we can compute the likelihood for one set of parameters, and then we can change the parameters, right? Change theta, run it again, so we can get different likelihoods based on our selection of parameters. Now, the data here is assumed to be independent, identically distributed, so it needs to have linear regression assumptions associated with it because we're doing regression. The other thing that's really important is that you have the same number of data points. And some people will say your data has to be identical to compare likelihood. I'm not sure that's exactly true, but you definitely have to have the same number of data points, because if you look at what happens, we've got to have the same number of multiplications, especially because these values, these p-values, can be very small when we're talking about complex phenomenon that we're modeling. In other words, the likelihood of each data point is going to be pretty small. Okay, so to illustrate this, one of the approaches that I've used in the past is to go ahead and take a fair coin and flip it. And if we take a fair coin and we flip it, let's say 20 times, we're going to get about 10 heads and 10 tails. Okay, so if we get 10 heads and 10 tails, and the probability of getting each of those is set to 0.5, then we're going to have 0.5 times 10 times 10. We're going to have, 0.5 times 10 times 10, or 0.5 times 20, because we're going to have 0.5 here over and over and over again. Not a good example. Let's say we do flip it once, we get 0.5. Another time we flip it once, we get 0.5. Now we have 0.25. Okay, so 2. Now, of course, you could flip it twice and get heads, twice and get tails. Well, anytime we flip it, we're going to get 0.25 if we flip a coin twice. All right, let's say we have an unfair coin. Let's say we have an unfair coin, or really a model that doesn't fit our data. Now we go ahead and we do a flip and we get heads. Hey, 0.8. We flip again, we get a tails, 0.2. Take a look at what happens. Instead of 0.25, all of a sudden we've got 0.16. So we don't have the maximum likelihood, right? Our likelihood is then 0.16 for this model, okay, where the other model it was 0.25. If we go to an extreme and say we've got a probability of 1 for heads, probability of 0 for tails, we flip a coin, we get heads, it's a 1. We get tails, we get a 0. Oops, our likelihood is 0. So with this model, we have 0 for the likelihood. This one we have 0.16, and this one we have 0.25. So this one shows to be our best model given the data. Now, there's an issue, right? If we just flip our coin twice, and we're using this model, we get a likelihood of 1. Suddenly that's quite a bit bigger than 0.25. So we could misread our model and how well it fits our data if we don't have enough points, don't have enough data points, or if we have a biased data set, right? Same thing with this. Suddenly 0.8 times 0.8 is 0.64. Well, that's better than 0.25. This must be the best model. So having a really good data set is critical to this process. So changing the model, calculating likelihood, and then picking the one with the maximum likelihood is the process of maximum likelihood. Okay? So we want to maximize this. Now, one of the issues is these piece of i's can get small. When you multiply them all together, they can get really tiny, like too small to compute. And they can happen pretty fast, especially with the big data sets we use nowadays. So what someone decided to do was take the natural log of likelihood and then multiply it times -2. Now, the reason to do that is because natural log doesn't get small as fast as the log does, or as the likelihood does. It also ends up producing this graph. You can go through, I just did this in Excel, but if we take -2 times the log of L, instead of having our probabilities get tiny really quickly, then we have this curve, whereas the probability increases, we get closer to 1. Okay, so in other words, as this value decreases, we get higher probability. So in other words, for -2 times the log of L, we're looking for the smaller value, the lower value. Okay, that's really important because when we flip over here to AIC, you will see here's our -2 natural log of L. We want that value to be small. In other words, a small value for -2 natural log of L is going to be a large likelihood. Okay, that's how we get maximum likelihood into here, even though it says -2. All right, K is the number of parameters. So now we have 2 times K, the number of parameters, minus, remember this will be a positive smallish number, okay? And we want to make this small. Well, we also want to make the number of parameters small. So now we've got two values that are really added together. Even though you see a negative, remember that this is a positive number here when we do the -2. So we add these together and we want them both to be small. That's how we get parsimony into AIC, or Akaike information criteria. You won't have to pronounce it. You will have to know this equation because it's really important. There is no equation in modeling that is more important than this equation because it's used the most widely. So again, 2 times the number of parameters plus a representation of maximum likelihood, okay, this number. But the math says -2 times natural log of likelihood, okay? Because we want to minimize this and minimize this to get our minimum AIC. And that's what you'll be seeing over and over again. So for AICs, smaller is better, but it's also only relative meaning. In other words, with one data set, you'll get AICs of 100 or 200. With another data set, you'll get the same model, different data set, you will get huge AICs, 70, 80,000. And that's again because of the way likelihood is computed. And we'll talk more about that. So what AIC achieves is this balance between complexity and what they refer to as bias. Now, I don't use that term in the same way all the time, so it's a different use of the term bias, but it's really about overfitting. Okay, so it's a balance between overfitting or modeling the errors / residuals and underfitting. Okay, so we don't want to underfit because then our model is missing part of the phenomenon that we're trying to model. It's too simple. If we overfit, then we're modeling the residuals as well as the phenomenon we're looking for. In either case, we're not going to have good predictive power. So in this case, we're going to end up with too many parameters. Sorry, so we're overfitting too many parameters. In this case, we end up with too few parameters. A couple of other things you're going to see. One is deviance. Okay, deviance is where we take and subtract the maximum log likelihood. Okay, notice it doesn't have the -2 in there. Okay, that's important. Maximum log likelihood for your current model minus max log likelihood for the most complex model possible. In other words, when the model fits your data perfectly. So since these are both negative numbers, we do this number will always be larger, so what's in the brackets will be negative. So again, they do the -2 thing, becomes positive, but bottom line is 0 fits the data perfectly. So if you have a deviance of 0, your model has fit the data perfectly. That doesn't mean it's a good model. It could still be overfit. Okay, and we'll see deviance this week, which is why we're hitting that. You'll also see degrees of freedom, n being the number of observations, p being the number of parameters, and degrees of freedom is n minus p. In other words, if you have 10 observations and you have 10 parameters, you have 0 degrees of freedom. Okay, it really means you totally overfit the data. Okay, so you don't want to have a 0 for degrees of freedom. Okay, that would be a bad thing. We don't have that happen too much with modern big data sets, but it does happen once in a while. Now, one of the problems with AIC is with big data sets, really quickly the likelihood values swamp it out. They're the ones that get really big. You could have 20 parameters in a model, so 2K is 40, and then you could have a likelihood that comes up to 50,000 because you've got 1,000 data points. So one of the problems with AIC is that it doesn't penalize overfitting enough, and AICC was an early attempt to fix that by adding this other parameter over here next to AIC, and that's AICC. You will see that. It's still not really enough of a penalty, so we still run into that, and we'll talk more about that. BIC is another one called Bayesian Information Criterion, and there's actually a series of these that have been done to try and improve upon this whole process. Okay, so that's AIC and its relatives. Now to talk about validation in general. So when we create a model, what we want to do is be able to validate it in some way. Now there's a number of different ways to do that, but you basically get your model, you evaluate it with AIC, you pick that as your best model, and then you're not done yet, okay? We want to be able to still beat on it. So we split it typically into test and training data sets. We train the data on one model, or train the model on one set of data, and then we test it or validate it against the test data, okay? And we can do a whole bunch of things to play with that to try and figure out how robust that is. I like injecting error into the response variables and the covariates. And that's we'll refer to as validation. You can also create maps. Of course, we're going to do our statistics with AIC and residuals. And then you repeat this over and over again. Okay, we'll talk more about that and summarize the statistics. Now, we're not going to do all of that this week. We're going to do that over the course of the semester, adding pieces because it's fairly complex. I introduce it now because students do struggle a little bit with the whole process, and this is a picture I've created to show you the whole process. In other words, here we've got our field data, here we have our sample data, here's our covariates, which may be part of the field data, but typically are separate. We combine those together to get our sample data. Now, if we're going to do validation, we split it, okay, into test and training. We use the training data to build our model. That results in our model. From that, we can do predictions using our predictors, which may be the same as our covariates. And out of that, we then get our predicted values. We can then validate those against our test data. Okay, we'll talk more about that. Then you create a predictive map, summarize your results, and then output your final statistics. And you can also do uncertainty maps if we repeat this process over and over again. Now, the repeating this over and over again and then introducing some randomness is going to be called Monte Carlo. We'll talk more about that. Okay, it's not called MCMC, Monte Carlo Markov chain. That's a different thing. You will see that misrepresented in papers. It is just Monte Carlo because it's named after the gambling casino where you go there over and over again with some randomness and lose money in southern France. Anyway, there's a number of steps here. Cross-validation is the most common, where you take and pull the data apart, and that's called cross-validation because you're using your own data across itself. Typically, we split it up in 70-30, train off of 70, test off of 30, and then repeat the process randomly splitting it up. And we'll go over some of these other ones over the course of the semester. Now, when you're finally done with this whole process, what you end up with is those charts we talked about before, scattergrams of your response versus independent variable, or histograms of the residuals. You'll end up with other charts. You'll have performance statistics. Again, they'll vary with your modeling method, but R² for linear, AIC, and deviance for most of the ones we'll be doing in the near future. And then you'll have your output raster with your, which is also called a modeled surface quite often in modeling. All right, so to get into the details of how we really go about doing this, we need to have a response variable, we need to have our independent variables, and for this, tables in comma-separated values and data frames work well. Okay, now we also need to have XY coordinates. We need to build the model from field or sample data, but then predict the output for the entire study area. Okay, so to start, we take our field data, which would typically have XY coordinates, and then some response value, some dependent value that we've measured in the field. We would then take rasters, like temperature layers, and extract values for the coordinates of where our field data are and add those. So now we've got our response variable and our independent variable together. We could do any number of independent variables. Together we use those as model parameters to then create our model. And out of that comes, out of that comes our performance statistics. Okay. Now, to be able to do a prediction in R, we also can take our independent variables, convert them to points, okay, and then add other independent variables if we need to a new data table, a new CSV. Okay, so these are two different ones. This one represents our entire study area. Then we use that to do a prediction. Our prediction is then added into this table or data frame, and then we take our prediction and use our XY coordinates to create our output raster. And this is what we'll be doing with R. And this is typical. There is a situation that arises, especially when we're dealing with just present points or occurrences. In other words, that's where we're getting our sample data and all we have is presence. So we don't have anything to regress against. Okay, this ends up with these kind of maps where you're like, it's just one value. We can't really do a lot with that. So what we need to do is we need to, we can build a model off of that, off of our presence points. Okay, but more likely what we're going to do is we're going to take our entire study area, convert it to points. So take one of our independent variables, convert it to points. Then we're going to build a new table that has presence and absence, or zeros and ones. In other words, where something was found and where it wasn't. It's going to represent our entire area. And then we use that to build our model, okay, result in our model parameters or our final model. Then we can use that against itself to then predict something like habitat quality for an entire area, okay? Now we're not going to do this too much because really we'll use Hemi or Maxent to do this type of modeling, but every once in a while we end up having to do this in R to solve a problem, so I threw it in here for you. This is by far the most common one, so take this, put it up on your wall, because we'll be doing this all semester.